Hi, everybody. This is Mechanics and Materials lecture for Wednesday, the 4th of February, 2026. So let's take a look at our Moodle page and see where we are and see if you have any questions to this point. All right, so we did homework number 1, and I've collected several of those homeworks. And then homework number 2 is what we're working on right now. So if we come down here to chapter 2, you'll see this is a 2-week thing. We started last week and we are continuing this week, but we are working through chapter 2, which are all of those really preliminary definitions of stress and strain and sort of all of the things that we need to have a basis for talking about mechanics of materials. Last time I also brought in my gear that had blown up because the kingpin, the shear pin was put in with too hard of a material. So the whole gear sheared off instead of just the pin. So that was kind of fun. But so the homework for chapter 2 is due February 8th, which is this coming weekend, Sunday. And then next week, we're going to start the quiz. Now, some of you know this, but if you have not worked with me with quizzes before, the quiz is not proctored. The quiz is kind of timed, I mean, within about an hour, but if you take a couple of extra minutes, it's not a problem as far as I'm concerned, but approximately an hour. It's open book and open notes, but it is not open neighbor. So you just have to take this in a quiet place. And what the real purpose of this quiz is to prepare you for the exam, which is coming up. So the quiz covers 2 chapters and is 1 problem with 5 different parts. And each one of those parts will be graded. The reason that I give you the parts is because I want to step you through the parts that you'll need to do on the exam. The exam is 2 hours, 4 problems. And although the same parts are implied, I don't explicitly ask you for them. So use the quiz as a guide for when you're taking the midterm exam. The midterm exam is not open book and open note. However, you get to bring in a single piece of paper, like a piece of engineering comp paper or something of that size, 8.5 by 11, and you can write on it front and back in your own handwriting as small as you want. You cannot photocopy anything, and you cannot have somebody with better handwriting write it for you. It has to be in your own handwriting. So I know I'm not talking to anyone in here. I've had well, one of them is my own son, but I've had students who their handwriting is basically illegible. And I remember the first kid that I had that had this kind of handwriting, not my son. When he would grab a pen, he would literally hold it like this and like etch into the, it was very intelligent, but I mean, his handwriting, the first time I looked at it, I kind of startled and I was like, ugh! And I thought, it looks like someone's holding a gun to his head, you know? It looks like this writing his own ransom note or something. And he says, I'm really sorry, this is how I write. And once you could decipher it, it was some really good stuff in there, but it was not pretty. So if you have that kind of handwriting, what I'm telling you is I have experience with that kind of handwriting, so I'm not the least bit worried about the quality of your handwriting. But so you will open the quiz here and you will take the quiz on engineering comp paper. And then when you are done writing on the engineering comp paper, you will scan it and submit it here. So in other words, you do not fill in the answers on the quiz tab. You open the quiz tab to read the quiz problems and parts of problems, and then you submit the same way that you do homework through the submit quiz tab. All right, so do you guys have any questions about that? All right, yes.
What is the question on? What are you gonna listen?
Oh, it's chapter 1 or chapter 2. So it's not, you know what I really like? All right, that's a good question, and I will answer that honestly. I really like stress on oblique surfaces. And I also really like strain within the elastic range before it starts to take on a permanent set. And so, and I'm also, of course, as you probably know by now, I'm not a stickler for turning things in on time, but I am a real stickler for units and significant figures. So all of that will be graded on the quiz. But if you've done the 2 homeworks, you will not find the quiz difficult. It's not, I always have, and I'm kind of saying this, you guys know, the people in the class right now know this because they've had other classes from me, but also for the benefit of the students who we've never been in class together before. I really mean it when I say you have to have the right number of significant figures or 1 off. I mean, like, if the answer should be 14.5 and you write 14.51, I might make a note, but I'm not taking up credit. If you wrote 14.5726498898, I'm just like, that has nothing to do with the measurement. And as an engineer, that's just a very important thing. So I'm very clear about that. I really want you to use the right number of significant figures. I really want you to use the proper units and to show me how you got the units if they're odd in any way. And then the other thing is mechanics and materials, especially, but all of the classes in general, you just have to draw a picture. That's how engineers work. We have a free body diagram or a stress diagram, and so much of it is in that picture. It's not just a picture, it's actually the work that you're doing. Kind of like we were just saying, Lucas, how a lot of engineers do not like to write very much. Which is absolutely true. Holy cow, absolutely true. However, we summarize things visually, and that's what we do with pictures. So there we go. That's kind of what we have going on. So we had talked about chapter 2, and I think we'd actually covered all of the material in chapter 2 last time. I mean, we talked a little bit about, I'm going to pull up the PowerPoint slides because we worked from the textbook last time. But like we said, what's the difference? Okay, here, I'll do a verbal quiz. What's the difference between stress and strain? Because like in real life, I heard this on TV last night. I was watching some show and she goes, "Oh, you've been under so much strain." And the guy goes, "Yeah." It's like, that's not what we're talking about, right? So what is stress and what is strain?
Stress is like a force of some sort, and then strain is more of how the material actually deforms.
Exactly. Stress is a force per unit area. And strain is a change in shape based on maybe a stress, maybe an outside load. Okay, so if you look at this, and this is available to you on your Moodle page, this slide pretty much goes through everything that we will need. We had talked about, let's see, I want to go through and make sure I cover this. Why do we care about this? Well, as engineers, I heard somebody once say, the art of engineering is doing with $1 in a day what anybody could do with $10 in a week. Okay, so I mean, how could we make everything strong enough for everything? Well, we could build it out of solid titanium, right? We could do that. We could, it reminded me of one of my cousins who's a mechanical engineer, used to work for a company called Magnetohydrodynamics, and they were looking for a particular kind of lining to a piece of equipment that had certain properties, and they'd been using copper, and it just missed the mark a little bit. So somebody suggested that they line the unit with platinum. Well, platinum was like at that time hundreds of times as expensive as copper. So you really have to weigh that against what you're doing. So we don't want to use platinum or titanium for everything. We don't want to build everything like you could land a helicopter on it. You want to design it appropriately and safely and still staying within economic control. So that's what this chapter is all about. Okay, normal strain. Normal, once again, another term, does not mean as opposed to abnormal. It means as opposed to transverse. Normal just means perpendicular. Normal strain is an elongation along the axis. And the axis is whatever is being pulled upon, generally speaking. And we talked about the stress strain gauges, which I just think are amazing. And we talked about the difference between ductile materials and brittle materials. And we discussed how things deform. Okay, whether a material is very ductile or interestingly ductile, these have different names, it's not really interestingly, but there is a place between 0 and some maximum yield sigma or normal stress, where this behavior, stress to strain, is approximately a linear relationship. And the slope of that line, because it goes through 0.00, because at zero stress, it should have no strain, right? I mean, if it is, there's something that's happened to it, we'll talk about, but if it's a new material, if you don't put any stress on it, it's not deformed. It's what you started out with. So the slope of that line is sigma over epsilon. And that number is referred to as the modulus of elasticity. So the modulus of elasticity only applies on the straight line or elastic portion, but it is a characteristic of the material. So in other words, if you know what the modulus of elasticity is, you don't really know what the material is, but you definitely know many things that it is not. So some things have the same modulus of elasticity, but they yield at different places, for example. So they're not exactly the same, but if it doesn't have a modulus of elasticity that you're looking for, it's something else. This is how brittle materials break. They do not stretch, they do not neck, they just break, pop, exactly. And this is what sigma versus epsilon stress strain diagram looks like for a brittle material. Pull on it, does not yield, it does not change, it just breaks. All right, so when we talk about the modulus of elasticity, what I said was the slope of this line, sigma over epsilon, and please notice there should be a sigma over here labeling this axis. That's a boo-boo. But all of these materials, quenched, tempered alloy steel of this particular number, high strength, low alloy steel, carbon steel, and pure iron, all have the same modulus of elasticity, but they yield in different ways and they yield at different points. So pure iron, as you can see, you reach yield and it barely, if you look at this, I'm just gonna show you those things. It barely yields and then it strain hardens and then it doesn't even really strain harden very much, just a bit, and then it breaks. Whereas these other materials behave differently, but the modulus of elasticity of all four is the same. Well, now that's an interesting comment right there, isn't it? In some other language, I had never seen that before. All right. I know. I don't know, something like that. So if a strain disappears when the stress is removed, the material behaves elastically. But if you've exceeded yield and you remove the stress, it may not go back to its original shape. It may have taken on a permanent set or a permanent deformation, which is what this line C to D indicates. It means even if you pull this particular material past yield and then you remove the stress, you still have a strain, meaning that the material has elongated or changed in some profound permanent way. Okay, so those are just some ideas about stress and strain. All right, so if you deform something with a normal stress with an axial load, you will have an increase in length in the amount of del. Del is in units of length. Strain is del over the original length L, so it is dimensionless. Epsilon, strain, is dimensionless. So it's the fraction of elongation or compression or shortening. I'm sorry, shortening is the correct word. So if you equate these things, you find out that del, this change, is equal to P, which is the load. P over A is the sigma, right? L, which is the original length, E. So PL over AE, this is something you will remember. E is the modulus of elasticity, which is the property of that material. So you can also see, since epsilon is equal to del over L, if you divide out L, you get epsilon is equal to P over AE. And if you work the units out, they come out beautifully. E is a big number. It's usually like 10 to the 6th if you're in PSI. So del is tiny because the elongation, unless you're dealing with silly putty or something, is not huge. But sometimes you'll have a double, like you might have a column with a different slender column made out of some other material underneath it, and you pull on it, you can use this as a summation equation. In other words, you can look at one bar and the other bar and then sum them and the overall del will be equal to the total of the two, or three or four, however many bars you put together. All right, here's an example. We have a bar here and a smaller bar here. We pull here and we pull here, push here, and we pull here. We are told what epsilon is, we're told diameter, and we want to find out the total deformation or the total del. Well, the first thing is, if you realize this wall is going to have a reaction, just like in statics, right? 75 minus 45 plus 30, that's 105, that's 60, right? So this is going to pull, the wall is going to pull back with a force of 60 kips. That means that this, if you do a cutaway, if you look at this section, it's going to be acted on with 60 kips. This is going to be acted on with 60 or 75 minus 60. This is going to be 60 minus 75 plus 45 and so forth. But you have to add the, I don't know if I added that up correctly. I have to go check my math. But basically, every time that you have a discontinuity, every time that you have a change in load, or a change in material, or a change in size or shape, you have to analyze those segments separately. Okay. All right, so there we go. So that's what they're talking about. Just like that. We have P1, blah, blah, blah. Do all the dels, add them up, and you get an answer. All right. And this is kind of the same thing. You analyze this kind of like, not exactly, it's kind of like a frame, not a truss, but you have to find those external forces. So you use those good methods of statics, which is why we did the review on trusses, so that you could do the method of section, method of joints, and remember how those internal responses occur. And then you come up with these answers. These are interesting. This is called, these problems, columns like this are statically indeterminate, meaning you cannot solve them based solely on methods of statics. If you have a column like this and it is fixed at the top and fixed at the bottom, it really can't go anywhere, right? So it can't really expand or contract. But if you pull on it, parts of it can expand and parts of it can contract. So the best way to think about it is, they call it superpositing, or using the method of superposition. You pretend like the bottom isn't here, and you analyze it as though it was allowed to deform however it wanted to. And then you add back in the deformation that the responsive force at the bottom has. And then you sum the total del to be whatever it is, 0. We also have some problems where the total del is not 0, but there may be a small gap that would be exceeded, and then it starts pushing back. So all of those things kind of, I don't know, they're interesting in terms of mechanics of materials, and they're interesting in terms of static loading. Okay, so you can see we have a del L and a del R, and we know that that has to equal 0. All right, so thermal stresses. Have you guys worked any problems with thermal stresses yet? Okay, what happens when you heat something up?
It expands.
Yes, exactly. What happens when you cool something down? Contracts. And it depends on the nature of the material, right? All right, so this equation tells you, if left to its own devices, if you heat up a material, and this delta T is always TF minus TI, so it's positive. Almost every material, there are some that are that behave in an unpredictable manner, but almost every material will expand if delta T is positive. In other words, if the temperature is higher than it was to begin with, it will contract if the opposite is true. Okay. Alpha is the coefficient of thermal expansion. Once again, alpha is going to be a characteristic of material. So different materials have different expansions based on thermal. All right, so we know that del due to a P, or a pull or a push, is equal to PL over AE, and we're told here that del due to a T is equal to alpha, that characteristic, times delta T times L. And so if you have something that is being pushed on and you have a thermal deformation, you can add them together and you'll get the total deformation. If it's constrained like this, what happens is, if you increase the temperature, it pushes against the support, pushes against both supports, but you can just envision it as being pushing against one support. So you use the method of thermal position to say, okay, thermally, it would expand this way, but really it expands nothing. So del sub P plus del sub T has to equal 0, or whatever, if there's a gap, it just fills in the gap. All right, and then we start talking about Poisson's ratio, which is another characteristic of the material. And what this means is if you have a bar of some sort and you pull on it on the axis, on the transverse section, it's going to shorten up, right? Because everybody has to be somewhere. So if you pull it long, it gets a little bit, it contracts a little bit. Poisson's ratio tells you how much that contracts. So, and it's always a negative. Pull on it, it gets smaller. That's why it's a negative value. All right, and this is generalized Hooke's law, which tells you if you have a cube in 3 space, right? This is just in 2-dimensional space. But if you have a cube or some structural element in 3 space, and you're looking at the change of length on the x-axis, which would be this way, but you have sigma x, sigma y, and sigma z. So in other words, you're pulling on it in 3 different directions. Sigma x is going to make it expand, but sigma y is going to pull it together a little bit, and so is sigma z. So this equation gives you Hooke's law in a generalized fashion, meaning the total epsilon x based upon the pull on the axis, on the x-axis, minus the pull on the transverse sections. Okay. So there you go. And then the bulk modulus, which is kind of the same thing. It's speaking to the same idea. All right. So I think that's probably enough for today because first of all, it's 12:46, and second of all, that's an awful lot of material. Do you guys have any questions for me? See, you're so smart. I just know what you're doing. All right. So I'll be around. I'm not going to be on campus tomorrow, but if you need something, send me an email or a text, and then I will be here all day Friday. So let me know what's going on, and we will keep wending our way through mechanics and materials. Have a great day and a great weekend.